In 1998, two competing teams of scientists set out to measure the universe's rate of expansion, using the light from its farthest galaxies with the help of the Hubble telescope. They began their investigations expecting to find the universe's expansion slowing down, on a path to stopping altogether, as matter on the inside exerts a gravitational influence which pushes back against the expansionary force, ultimately destined to bring the universe into a collapse. However, when the teams analysed the light from our observable universe's farthest galaxies, both were stunned to arrive at the same conclusion. Space is not only expanding, its expansion is accelerating. The rate at which space is growing has been picking up pace over time, despite the enormous contractionary gravitational influence exerted by the cosmic web. What this means is that, if the energy of gravity is insufficient to pull the universe back together, then there must exist an additional, hidden part of the universe's energy which pushes outwards, in a way that can overcome gravity on the largest scales. The source of this mysterious energy underpins our topic today. It represents one of the biggest astronomical mysteries of the last 2 decades, and understanding its nature may just help us to know where this universe is headed. It is the mystery of dark energy. Dark energy is the term given to a mysterious, unknown portion of the universe's energy, not classifiable as matter, radiation, or dark matter, which is attributed to the accelerating expansion of space. Like dark matter, dark energy has never been conclusively proven or directly detected. Rather, its existence is inferred through the behaviour of space on large scales. There is compelling evidence to suggest that our universe has expanded more in the latter half of its life, particularly picking up pace within the last 5 billion years or so. And if this is the case, then there simply must be an additional type of energy in space which pushes outwards to drive it. If matter, radiation, and dark matter were the only energies in the universe, then gravity would be the dominating force, exerting an attractive influence which would ultimately cause the universe to shrink. The fact that we are seeing the opposite of this, in spite of the tremendous gravitation of the cosmic web, suggests that more than twice as much energy must exist in the form of an anti-gravity force, which has negative pressure, a dark energy. In the absence of gravity-inducing mass, dark energy exerts a repulsive force, manifesting in the form of tension on space. On local scales, this tension is vanishingly weak, analogous to a grain of sand per Earth-sized volume of space. Therefore, even the slightest gravitational influence is enough to suppress dark energy's effects and nullify expansion. And thus we don't feel its influence anywhere where there is a significant gravitational field, like Earth, the solar system, the galaxy, and even our entire local galactic group. However, this stuff is theorized to fill up all the space between galaxies, and on the largest macro-universal scales, the cumulative effect of this negative pressure tension is what is believed to be accelerating the growth of space, contributing to 9% greater expansion and rising. Aided by dark energy, the universe is now doubling in size every 10 billion years or so, but to what end, nobody knows. The simplest interpretations of dark energy describe it to be a consistent, intrinsic property of empty space itself. not an energy field, but rather an energy density, an ever-present rate of rest energy for the near vacuum of space. This idea traces its origins all the way back more than a century, to Albert Einstein and his 1915 general theory of relativity. General relativity is a comprehensive description of gravity, the nature of space and time, and their links, whose predictions have held up after more than a century of scrutiny, which is ironic considering that they were conceived upon a fundamental misconception about space. At the time of the theory's publishing, scientists like Einstein believed the universe to be static. They hadn't yet accepted the notion of other galaxies and viewed space to be a boundless, ageless expanse of scattered stars and nebulous gas in every direction. But Einstein knew that such a universe would not simply stay static on its own. The gravity induced by the matter on the inside would exert an attractive influence which, if left unaccounted for, would cause space to contract. In order to achieve a balanced universe which neither expands nor contracts, space would require its own anti-gravity-like force to neutralize this collapse. And so, in 1917, Einstein amended his theory of relativity to include the cosmological constant, a measure of the repulsive vacuum energy of empty space, denoted by the Greek character lambda. Einstein derived a very specific solution for this constant, which would have been mathematically just enough to bring a contracting universe full of mass and gravity to static equilibrium. However, discoveries in the years that followed did not support the notion of a static universe. In 1923, we realised that other galaxies existed outside of the Milky Way, and by the end of the decade, we'd realised that the space around these galaxies is expanding. It soon became apparent that Einstein's model of an endless, unchanging cosmos was unsatisfactory, and in 1931, he finally refuted his static universe model with the cosmological constant, taking it to his grave as the greatest stupidity of his life. He then teamed up with fellow mathematician Willem de Sitter, spending the next year developing a new model of an expanding universe with the cosmological constant set to zero. The notion of lambda itself was never fully thrown out. The final nail in the coffin of the static model was undoubtedly the discovery of the expanding universe, one of the most important discoveries of all time. The notion of cosmic expansion was first proposed by Georges Lemaître in 1927, and was later confirmed through follow-up observations by Mount Wilson astronomer Edwin Hubble, using the world's then largest telescope. By plotting the motions of 24 newly discovered nearby galaxies, Hubble found a linear relationship between their radial velocity and their distance from Earth. In other words, Hubble found that the further away a galaxy lies, the faster it appears to be moving away from the Earth. His conclusion was that space itself is inflating, in a way that carries galaxies ever further apart from one another. As if we were ants standing on the surface of a balloon, when empty space expands, it expands pretty much everywhere, stretching apart in every direction to make more space, widening the gaps between galaxies over time, though leaving the galaxies themselves unaffected. Every single second, our universe's volume increases. The Hubble constant is our measure of how much it is growing by, per second, per unit of volume. This figure has been the subject of a decades-long scientific pursuit, with a number of varying techniques used to arrive at differing estimates. For a long time, scientists couldn't agree on a meaningful prediction, but all that changed with the launch of the Hubble telescope, Despite a bumpy first few months of operation, the telescope was soon installed with the capacity to see all the way out to the edge of the observable universe, finally giving us a wide enough field of view to constrain our first precise estimate, 72 kilometers per second per megaparsec. A megaparsec is a unit of space equivalent to 3.2 million light-years. This means that the space within our immediate extragalactic neighbourhood is being stretched at a rate of around 72 kilometers a second, relatively insignificant on a scale of 3 million light-years. In fact, the Milky Way and Andromeda galaxies are actually being drawn together faster by gravity, allowing them to collide in around 4 billion years, overcoming the local force of expansion. However, the Hubble constant is compound, 72 kilometers per second per megaparsec. This means that, for every 3.2 million light-years further from the Earth we look, the galaxies in that space appear to be receding another 72 kilometers a second faster. And so, for those distant galaxies outside of the local group, lying dozens of megaparsecs away from the Earth, it becomes very easy to rack up recessional velocities of thousands of kilometers per second relative to the Earth, some so fast that they appear to be receding faster than light speed, though this doesn't break any laws of physics because nothing physical is moving that fast. The expansion of space has a distinctive effect on light travelling through it, causing it to appear redshifted after a considerable intergalactic journey. This is because light travels in waves, which are emitted omnidirectionally into space from a luminous source, and the frequency of the wave patterns defines the type and intensity of light when it reaches the Earth. But as these waves travel across very vast intergalactic distances, the cumulative expansion of the space they are travelling through slightly stretches out and separates these wave patterns, decreasing their photon energy and shifting them towards the lower energy end of the electromagnetic spectrum. For visible light, this has the effect of turning it red and making it dimmer, hence the term redshift. Therefore, by probing the redness of deep intergalactic objects, we can determine how much the universe has expanded since those photons were first emitted. And if we do this for a wide enough range of distances, using a telescope like Hubble, we can plot the trend in the rate of expansion over time. The problem is, we can't use galaxies themselves to accurately measure redshift values, because galaxies vary too significantly in their luminosity and surface brightness. What we really need is a standard candle, something with a consistent, known luminosity which we can compare to its apparent brightness to reverse engineer a distance. But then, what else besides a galaxy is both common enough in space and consistently luminous so as to elucidate 10 billion years worth of cosmic history? We can't use quasars, because they also vary unpredictably in luminosity and apparent brightness. And so instead, we need to look to supernovae. And not your conventional type of supernova caused by the collapse of a dying star. Those explosions aren't nearly luminous enough to shine across the vast universal distances we need, but a Type 1a supernova is. The Type 1a is the brightest class of supernova there is, occurring in binary star systems with one or more white dwarf stars. White dwarfs are the exposed cause of sun-like stars, not massive enough to go supernova when they run out of fuel. Rather than exploding, smaller stars simply shed their outer layers, revealing their internal crystallizing core in the process, a planet-sized sphere of mostly carbon and oxygen matter, but not in the quantities required to sustain nuclear fusion. As such, lone white dwarf stars can remain stable for quadrillions of years, never fusing their internal fuel. However, if a white dwarf exists in a binary star system, where it has a giant, late-stage stellar companion that is ejecting material, then the story is not quite so simple. In this case, some of the ejecta lost by the accompanying star will be accreted by the white dwarf, growing its mass in the process. But the heavier a white dwarf becomes, the less stable it will be, until it reaches a deadly mass threshold at which it becomes the ultimate nuclear bomb. Above this critical mass, known as the Chandrasekhar limit, a runaway thermonuclear process will ensue which reignites fusion within the dwarf star, causing it to explode in the most energetic and incandescent type of supernova there is, creating a flash so bright it can outshine its entire host galaxy. And because these explosions always occur at the same mass threshold, about 1.44 times the mass of the Sun, roughly the same amount of mass is invariably converted into energy in the same way, giving this class of supernova a common peak luminosity. And because they occur in galaxies dotted right around the universe, they make the perfect standard candles for measuring redshift values. With this in mind, in 1998, those two teams of scientists we mentioned at the start, the Supernova Cosmology Project, headed by Saul Perlmutter, and later on, the High Z Supernova Search Team, led by Brian Schmidt and Adam Rees, used these distant Type 1a supernovae as standard candles to measure the rate of the universe's expansion. As we mentioned, both teams initially expected to find the expansion rate slowing down, as the self-gravitation of the cosmic web bites back against the expansionary force. This would be the expected behaviour in a universe where matter, dark matter and radiation are the only energies in space. And for a period between 4 and 8 billion years after the Big Bang, the universe's expansion did appear to be decelerating as predicted. However, when these two teams looked beyond the boundary of Redshift 1, they found that the deepest Type 1a supernovae all appeared to be somewhat redder and dimmer than would be expected if the universe really were slowing down. On the contrary, it appears that the universe's expansion has actually accelerated within the last 5 billion years, casting the farthest Type 1a supernovae that much further away from the Earth. Both supernova search teams concluded that the universe's expansion is accelerating, not slowing, and thus gravity must not be the prevailing force on macro-universal scales. Both teams agreed on the need for an additional, repulsive type of negative pressure energy in space to drive this acceleration, and within that same year, a paper on the topic issued by the High Z Supernova Search Team invoked Einstein's long-rebuked cosmological constant to describe this missing energy, which quickly became known as dark energy. Suddenly, what Einstein died believing to be his greatest blunder was right back in the frame. This revelation prompted scientists to revisit their old models of cosmology in favour of new ones which invoked additional energetic components. Long before this, in the 1980s, scientists sought to explain how a Big Bang could have given rise to the cosmic web in under 14 billion years, with only the energies of matter, radiation and dark matter. They found that cosmological frameworks containing 95% cold dark matter and 5% normal baryonic matter went some way to explaining how galaxy clusters could have formed, but couldn't account for superclusters on the scales we see today. And the problems plaguing the original cold dark matter models of cosmology only increased in the 1990s, with the discovery of anisotropies in the cosmic microwave background radiation. This led scientists to rethink their models of the Big Bang and develop several new parameterizations. Some of these frameworks, in particular lambda-CDM, invoked Einstein's cosmological constant as a measure of the energy density of space, either on theoretical grounds or by mathematical necessity. But it was only when the need arose for an additional type of energy in space to explain cosmic acceleration that lambda-CDM raced to popularity, establishing itself as the standard model of astrophysics in the early 2000s. And today, this model constitutes the science we teach in classrooms and lecture theatres. The model describes dark energy as accounting for little under 3/4 of the universe's energy density, with dark matter adding another 23%, and the rest, the stuff we can observe, making up the measly remaining 4%. And as the expansion of space has diluted other energy densities, dark energy's constant presence has gained an ever greater foothold in the universe's behaviour. And around 5 billion years ago, this energy became the dominating influence on universal scales, propelling the universe into the dark energy dominated era, which is ongoing to this day. In the past 2 decades, we've attempted to search for signs of both dark matter and dark energy, with little success in either endeavour. However, while a wealth of elaborate and sophisticated dark matter detecting experiments exist, there have been far fewer dedicated dark energy initiatives. As is the case with dark matter, we are limited to detecting only indirect evidence of dark energy's existence. At a rate of 1 grain of sand per Earth-sized unit of volume, it propagates far too negligibly on galactic scales for any instrument to directly observe. Alas, we can only infer its existence, either from optical observations of Redshift, or by studying the patterns on the CMB. When it comes to probing Redshift values, most of the research into dark energy has been performed using NASA's Great Space Observatories, particularly the Hubble and Chandra telescopes, as well as a handful of ground-based observatories like the 2DF Galaxy Survey. Alternatively, we can study the cosmic microwave background radiation to gain a non-optical perspective on dark energy. As a snapshot of the universe from when it was just 379,000 years old, this relic radiation provides a starting configuration for the young universe, which we can compare to the space we see around us today, providing another angle for measuring cosmic expansion. Several missions, most notably NASA's Cosmic Background Explorer, its Wilkinson Microwave Anisotropy Probe, and more recently, the European Space Agency's Planck satellite, have mapped this ancient radiation in ever-increasing detail, revealing its tiny temperature fluctuations, also known as its anisotropies. The CMB's anisotropies provide their own means for studying dark energy, as they reflect the universe's structure in a much less expanded state. Instead of the branches of the cosmic web, we see baryonic acoustic oscillation patterns, sound waves which occurred in the universe's early photon baryon fluid. As we covered last time, shortly after the Big Bang, the universe was flooded with an ocean of interlocked matter and radiation. As the gravity of its mass tussled with the pressure of its radiation, acoustic soundwave patterns propagated through the fluid-like plasma, resulting in slight imbalances in its density. Then, When this plasma condensed to form atoms at the moment the CMB was created, their distribution mimicked these imbalances, leading to areas of enhanced mass, which are reflected by the red, warmer areas of the CMB. These warm areas, where atoms were concentrated by oscillations, have today evolved into vast galaxy clusters and filaments. And thus, just as a supernova can be used as a standard candle for measuring expansion, a baryonic acoustic wave pattern in the CMB can be used as a standard ruler, whose dimensions can be compared to its present-day correlating galaxy cluster, allowing us to trace its expansion from point A on the CMB to point B in space. This allows us to map exactly how the space within galaxy clusters expands, and when combined with our observations of Redshift, they enable us to loosely constrain some of dark energy's expansionary properties. And over the next decade, several new groundbreaking observatories will take to the skies. The recently activated James Webb Telescope will soon undertake missions aimed at studying both cosmic acceleration and dark energy, as it becomes astronomers' tool of choice for studying the farthest redshifted corners of the universe. And next year, in 2023, the European Space Agency is poised to launch its own next-generation infrared observatory, Euclid, which will investigate the mysteries of both dark matter and dark energy. And then later in the decade, possibly 2027, NASA will launch its own dedicated dark explorer, named after the mother of Hubble, the Nancy Grace Roman Telescope, formerly WFIRST. Like Euclid and James Webb, the Roman telescope will peer into the deepest recesses of the universe, undertaking its own studies of galaxy clusters, redshift and baryonic acoustic oscillation patterns, aiming to bring us closer to a complete understanding of the phenomenon. A common goal of these missions is to constrain one particular parameter for dark energy, its equation of state, the ratio of its outward pressure over its inward density, determining the amount of influence dark energy puts on the cosmos, represented by the lowercase Greek character omega. As we mentioned, dark energy has negative pressure, and thus scientists take this value to be less than 0. But exactly how much less will determine how dark energy behaves in the long run. Specifically, whether its density will remain constant over time, or whether it will vary as a function of time. And each possibility carries a different theoretical nature for the phenomenon. The simplest interpretations of dark energy, including the one implemented by lambda-cdm, take omega to be bang on -1. In this case, dark energy would have a constant, unchanging energy density over time, describable with Einstein's cosmological constant. If this is true, then it weighs in favour of dark energy being an intrinsic rest energy of empty space itself, not a variable force like gravity, but rather a baseline rate of energy for the near vacuum of space. But to understand how empty space can have energy, we need to venture into the confusing realm of quantum physics. In quantum terms, even the space in a vacuum has its own complex structure, characterized and permeated by all the quantum fields that exist within in their lowest energy states. But even in ground state, these fields still exhibit so-called zero-point fluctuations, as they randomly flicker between minimal energy and no energy. In practice, this is thought to be caused by tiny pairs of virtual particles and antiparticles, which pop in and out of existence on scales far too small and brief for us to observe. These virtual particle pairings inevitably latch onto one another and annihilate themselves instantly, emitting a tiny quantity of zero-point energy in the process. This energy manifests in the form of outward pressure, but goes unnoticed within galaxies as it is easily muzzled by gravity. However, the cumulative effect of these vacuum fluctuations occurring within all the empty space between galaxies is thought to be what is inducing the accelerating expansion of the universe. This is widely viewed as the most compelling explanation for constant dark energy's nature. However, when scientists tried to test this theory by summing up the rest energies of all the quantum fields which are known to exist in space, the results were 100 orders of magnitude greater than what would be necessary to drive a relatively recent period of minor acceleration. Theoretically, vacuum fluctuations would give rise to far too much dark energy, resulting in significantly enhanced cosmic expansion, fundamentally warping our view of the surrounding universe in the process. This glaring discrepancy between prediction and observation is known as the Cosmological Constant problem, and remains one of lambda-CDM's most troubling mysteries. However, the issue is often overlooked by standard cosmologists, as the lambda interpretation of cosmologically constant dark energy works well enough for explaining many of its other observed behaviours. Furthermore, independently constrained estimates from both the Chandra telescope and the Planck satellite have found omega to be very close to -1, implying a near constant energy density. But even a small discrepancy either side of the -1 fence would necessitate a different theoretical explanation for dark energy's nature. If the omega value lies slightly above -1, but below -1/3, for example the -0.99 value derived by the Chandra telescope, then it would mean that dark energy's density is actually falling over time, like the densities of matter and radiation, implying that dark energy may be a new fundamental force. This branch of theories is generally known as quintessence, from the Greek meaning fifth element, and they describe dark energy as a fifth fundamental force, working independently from gravity, electromagnetism, and the nuclear forces. This force manifests as a weak, variable quantum field with both kinetic and potential energy, and its ratio of the two determines whether it attracts or repels. Unlike lambda, quintessence interpretations describe dark energy's density to be dynamic as a function of time. The K-essence model, in particular, predicts dark energy's density as being closely tied with the falling density of radiation. Hence, around 3 or 4 billion years into the universe's life, the density of radiation fell below a threshold at which the associated quintessence field began behaving like dark energy, exerting an outward pressure that pushes back against gravity, eventually becoming prominent enough to drive late-time cosmic acceleration. This interpretation is regarded as the principal challenger to the standardized view of cosmologically constant dark energy, offering solutions to some of the aforementioned persisting problems, such as the cosmological constant problem. Thus, there exist quintessence cold dark matter models, or QCDMs, to rival lambda-CDM, supposing that dark energy's omega value lies slightly above -1. Those theories that hold this value to be the other side of the fence, below -1, are known as phantom energy, because they suppose that dark energy's density is increasing over time, with more coming into existence unproportionally to the universe's scale factor. While this nature is viewed as the least likely of the three outcomes, it would have seismic implications on the fate of the universe if true, as it would mean that space becomes so crammed full of dark energy that it risks tearing apart altogether. This would completely destroy the ever-expanding universe in an event known as the Big Rip, one of 4 possible ways our universe is theorized to end. The Big Rip hinges upon the existence of phantom dark energy, whose density increases over time as other energy densities fall. If dark energy's density increases over time, then so too will the strength of its negative pressure, driving the universe to unfathomable sizes. As we covered earlier, right now dark energy's anti-gravity force is not nearly substantial enough to affect gravitationally bound structures like our galaxy. However, if its influence is increasing over time, then eventually even galaxies will succumb to the expansionary force. Phantom dark energy would see its strength increase so much, in fact, that even atoms themselves would dissolve down and disperse under the unimaginable stretch of near infinitely expanding space. The time these events would take to unfold depends on how far below -1 the true omega value lies. If it sits only slightly below, for example -1.028 as estimated by the Planck satellite, then the Big Rip would happen eventually, but only after an implausible amount of time. But let's say, for example's sake, that the true value is actually -1.5. Then the Big Rip would happen in around 22 billion years, though its most destructive effects wouldn't be felt until relatively near the end. In the final 50 million years before the Big Rip, galaxies would be irreversibly separated from each other, causally disconnected by intergalactic distances which are expanding faster than light speed. And from this point, even the galaxies themselves would start to break down. Over tens of millions of years, stars would gradually be lost over the cosmic tide, until galaxies are dispersed entirely, and even stars themselves are causally disconnected, confined to their own pocket of ever-expanding space larger than our entire present-day observable universe. In the final 3 months before the Big Rip, these last surviving stars would feel their planets plucked from their circular orbits, before long separating all celestial bodies from one another. In the final minutes, even the stars and planets themselves would start to disintegrate as they are pulled apart into individual molecules and atoms. Then, in the last nanosecond, even atoms themselves would break apart, as phantom energy's exponentially increasing strength exceeds that of the strong nuclear binding force between atoms. This would result in such aggressive, unstoppable expansion that each resulting subatomic particle would then instantly be cast into its own area of near-infinite space, destined to never meet another particle. And then finally, at time zero, the distances between these particles would become infinite, along with the rate of expansion. Space would inflate so much that it tears completely, removing all boundaries and constraints and turning universal distances infinite. The universe would pop out of existence like a burst balloon, and time would stop forever. And with that, the story of the phantom energy-dominated universe would be over. Thankfully, most scientists disagree with the notion of a Big Rip, because it would require dark energy to arise out of nothing, violating the laws of thermodynamics and the principles of general relativity. And thus, we believe the universe will simply continue to expand forever, never explicitly ending, but becoming homogeneous and brain-dead as its entropy reaches maximum, in an event known as the heat death or Big Freeze, another one of the 4 predicted paths to universal oblivion. However, this more likely ending for the universe is forecast to take around 10 to the power of 100 years to occur, and so we have plenty of time to continue the study of dark energy in the meantime. With several next-generation experiments on the way, it seems almost inevitable that, over the next decade, we will get a better idea of where our dark energy-dominated universe is heading.